and start sharing the screen and start with today we're going to do a little bit more factoring. I have a few more examples, a little bit more notes that I'd like to give you. And if I remember correctly, last class I got booted about a half an hour before the end of class off of Zoom, and then it happened again 20 minutes later. And the first time I went back in, everybody was there and life was good. The second time I went back in, and wherever it took me, there was nobody there. So I have to apologize that we ended abruptly last class. It was solely a function of the internet connection that I'm using. I'm very sorry about that. So we'll pick up kind of from a little bit before where I left off, because I don't know how soon you guys lost me. So we'll be doing more factoring. P5 is on factoring. That will be due on the 17th. I think everybody knows that the 15th is a holiday. There is no class. So the next class is the 17th. P6 is on rational expressions. We'll start doing a little bit of introduction to that today. In addition to those homeworks, there's a problem set. The problem set counts as a quiz grade. You don't have to submit your work with that one. You can take it over and over and over again. It counts as a quiz grade. In practice, what it is a practice test. And so we will go over that hopefully on the 19th. And that first test will be available between the 19th and the 21st for you folks to take. If everything continues on schedule, that's the tentative due dates for all of that. Before we start picking up with where we left off, just before I got disconnected from you folks, does anybody want to look at any homework questions? Does anybody have any concerns with any homework problems? Does anybody want me to go over any of them?
I'm good.
Okay, I've waited long enough. So then we had been looking at factoring. We had spent a good bit of time factoring trinomials. We had perfect squares, where if it began and ended with a perfect square, we knew what to try first. We had trial and error. And we had that AC grouping method. We spent a lion's share of our time looking at those last class. And so I'd like to start with just a couple of examples and ask you folks to please factor each. And let's look at 4x squared plus 16x plus 15 and 9x squared minus 27x plus 20. And again, I'm going to give you folks a minute to look at those two, and we'll go over. And I guess we'll go over one by trial and error and the other by the AC grouping method. So I'm going to just shut up and have you folks do those. How are you folks doing? Are we ready to go over yet or no?
Yeah, we're ready.
Okay. I'm going to look at the second one first because I think the second one is easier to do by trial and error. For 9x squared, I could have 1x and 9x, or I could have 3x and 3x. For 20, I could have 1 and 20, 2 and 10, or 4 and 5. And so playing with these numbers, knowing that I'm having the same sign, if I look at the 3s and the 4s, well, 4 and 5, 3 times 4 is 12, 3 times 5 is 15, 12 and 15 will give me that 27. And so when I try the 3x minus 5 and the 3x minus 4, first is my 9x squared, outer is my minus 12x, inner is my minus 15x, last is my plus 20, and I nailed it. The first one, if I were to try this with the AC method, A times C would be 4 times 15, which is 60. And so I'm looking for numbers that multiply to 60 and add to 16. So I'm thinking of 10 and 6. So I rewrite that as 4x squared plus 10x plus 6x plus 15. And when I do grouping, the first two have 2x in common, leaving me with 2x plus 5. The last two have 3 in common, leaving me with 2x plus 5. And so my common factor is 2x plus 5. And the other factor would be 2x plus 3. Again, which method you use really depends on your own personal preference. But you need to grab one or both and kind of become masters of the universe with it. We did a lot of factoring trinomials last class. I'm just doing those quick examples to kind of get your heads in the same place. Then we started looking at binomials. And we had said that binomials could be the difference of squares. And the difference of squares would be something like 121x squared minus 25. 121x squared would be 11x quantity squared. 25 is 5 quantity squared. And we had said that that factors into the sum and difference of those roots. So I'll have 11x plus 5 and 11x minus 5. One more. Let's look at 64x to the 4th minus 4. And whenever we factor, which I didn't look at with the preceding examples because I have to apologize, I should have mentioned it, but I didn't because I knew it didn't apply, is whenever we factor, we're always going to ask, is there something in common? And is there something in common between the two terms of this binomial? Is there a number that goes into both 64 and 4? 4. And so when I factor out that 4, that leaves me with 16x to the 4th minus 1. Oh, okay. This is a perfect square. That would be 4x squared squared. 1 is a perfect square. That would be 1 squared. So that gives me 4 times, it would be what, 4x squared plus 1, 4x squared minus 1. But a lot of the times when you see these directions, they don't say just say factor, they say factor completely. And when I hear that factor completely, it's usually a hint that there's a good chance you might have to factor more than once, which we did already. We did the common factoring, and then we looked at the difference of squares. But as I look at my factors, okay, 4, that's just a constant. We're not going to worry about that. Okay, this one, it's 2 terms with a plus sign. They're both squares, but it's a plus sign. I can't do anything. But does everybody notice over here I have the difference of squares again? The 4, the common factor stays. The one with addition I cannot factor. But the one with subtraction, can't I say, well, 4x squared is 2x times 2x. 1 is 1 times 1. And again, for that to be negative, I need the sum and difference. And so the final answer would have to be all of that. And again, that's just a little bit of review of what we had done on Wednesday. Everybody with me? Can you guys hear me?
Yeah.
Okay. Where we started breaking up was with the sum and difference of cubes. And this is where I don't know how much you folks did or didn't hear. If I have 2 cubes, a cubed plus b cubed with addition, or a cubed minus b cubed with subtraction, I would love to show you why this applies, but in order to verify this, in order to prove this, we would need to do long division, and we haven't covered that. So I hate saying this, but it's a pattern you've got to know. We did the multiplication for one of them in early problem when we were multiplying a binomial by a trinomial. Over here, if I have a cubed plus b cubed, the first factor is a plus b. Notice they have the same sign. Then the other factor, well, it's going to start with a squared and end with b squared. That's how I get those cubed. Those will both be positive. But over here, we're going to have a middle term of negative ab. And please notice these signs are opposites. Instead, if I have a cubed minus b cubed, it's going to start with a minus b. That trinomial, again, we're going to have a squared and b squared, but the middle is going to be addition. And so with these, you need to remember whatever I'm cubing, first I'm going to take either the sum or difference of those. That is the first one squared, just the product of the two, the last one squared. And these will always be opposite signs. And so if we look at some examples of those, let's say, for example, I have 2z cubed minus 16. I have a z to the third, but neither 2 nor 16 are cubes. But wait a minute. Didn't we always say no matter what we were factoring, the first thing we were going to ask is there anything in common? Do these two terms have a common factor?
Yeah.
2.
What? 2. So when I take out the 2, then I've got z cubed minus 8. And I think it's obvious that z cubed is a cube. And does everybody recognize that 8 is 2 to the third? So I'm going to keep my common factor of 2. Here, what I cubed to get is z. Here, what I cubed to get 8 is 2. And then following that pattern, I want to square the last one that first one, pardon me. I want to square the last one. This is subtraction. The opposite is addition. And I'm going to just take the product of those two. 99.9% of the time, this remaining trinomial will be prime. It does not factor further. And so this will be your final answer. So another example, let's say I have 3y to the 6th minus 81. Is there anything in common?
Yeah.
What? 3. Dividing out that 3, factoring out that 3, I'm left with x to the 6th minus 27. And does everybody recognize that x to the 6th is a perfect, I'm sorry, y to the 6th. Y to the 6th is a perfect square, but it's also a perfect cube. And 27 is 3 to the 3rd. So we'll keep our common factor of 3. The cube root of y to the 6th is y squared, minus the cube root of 27 is 3. Then we're going to take that y square and square it. We're going to multiply 3 times y squared. Because this is subtraction, we have to add it, opposite sign. And then we're going to also add that last one squared. 3 squared is 9. And the last example I think is really fun. But one semester I did try to teach this course with an OER, an open educational resource, and it broke my heart breaking away from them because that was the material that was free for students. But there were a couple of questions like this one where I had major problems with the way the OER treated it and graded it. And so they were accepting wrong answers as right and the right answers they were not accepting. And students were getting so frustrated that I ended up, that was the last time I ever used that open educational resource. And I haven't seen another to compensate for that. So over here, everybody recognizes that I have a binomial, I hope. Hopefully everybody recognizes that there are no common factors. First, I'm going to ask myself, are they squares? Well, even exponents are squares, and 64 is a square. So what do I square to get x to the 6th? X to the 3rd. What do I square to get 64? 8. One's addition, one's subtraction. What I think is nifty about this question is now when I look at what's left, I have cubes. So x to the 3rd plus 8. The cube root of x to the 3rd is x. The cube root of 8 is 2. That's a plus sign, so this is a plus sign. Square the first. Subtract the product. Square the last. And now here I've got the difference of cubes. X cubed is x to the 3rd minus 2 to the 3rd is 8. Square the first. Opposite sign. Take the product. Square the last. And so that'll be my final answer. How fun is that? You guys sound thrilled.
Yay.
Yay. Okay. So, real quick, looking at, I'm going to give you folks what's my factoring checklist. Whenever I'm told to factor or factor completely, the first thing I look for is a common factor. Then the second thing that I do is I count the terms. If there are two terms, I look for the difference of squares. Or I look for either the sum or difference of cubes. If it's neither, we're not going to be able to factor it. If there are three, I can use trial and error. I can use that AC grouping. And if it starts and ends with perfect squares, I can always keep an open mind and watch for the perfect square trinomial. If there's four, we said we'd usually use grouping. But sometimes grouping does not work for four terms. Whoa. My hand is not keeping up with my head. I'm sorry. Sometimes four terms is not grouping. What do I mean? Let's look at x squared plus 12x plus 36 minus 49y squared. And if I were to split this down the middle, these have nothing in common. It does not help. The first two, I could take out that x, but there's no way I'm going to get that x plus 2 in the second ones. And so instead, I notice that this last one is a perfect square. And so I look at these first three. And what we need to be able to do, seeing that it starts with x squared, I'm sorry, that 2 should have been a 12. I recognize that it's a perfect square trinomial. That turns out to be x plus 6 quantity squared. And now I have the difference of squares. And so that'll be x plus 6 plus 7y times x plus 6 minus 7y. I have to apologize. I guess I went a little crazy with the parentheses in the first one. How fun is that? And so I'd like to give you folks one like that to try. Let's look at x squared minus 10xy plus 25y squared minus 81. And it's going to work in a manner similar to the one we just did. So I'm going to give you guys a minute. Did anybody else get x minus 5y minus 9 and x plus minus 5y, pardon me, plus 9? Shall we add the details?
Yes.
Okay. I'm looking at these first three. This trinomial. This is a perfect square. That would be x squared. This is a perfect square. That would be 5y squared. I'm going to put a minus sign in the middle. And I'm going to think of that as x minus 5y squared. If you want to check, we can take x minus 5y times x minus 5y. First, x squared, outer, minus 5xy, inner, minus 5xy. Last, plus 25y squared. So that gives me that x squared minus 10xy plus 25y squared. Or the other way you could check is you can think, well, if I take x times 5y and double it, won't I get that 10xy? So that's a perfect square. And then 81 is a perfect square. That's 9 squared. And so now what I have here is the difference of squares. So it'll be the first one plus the root of the second and the root of the first one minus the root of the second. And because multiplication is commutative, either one of those works. And then before we go ahead and start defining and looking at problems involving rational expressions, I'd like to just give you a couple more challenging factor practice questions, if everybody's all right. So we're going to factor each. And let's start with x minus y to the fourth minus 16 times x minus y squared. If you're a glutton for punishment, you're going to multiply all of that out. But it's written in this format for a reason, and we shouldn't need to. Is there anything in common between the two parts? Does everybody see a common factor of x minus y? And the lowest exponent on that common factor is 2. So when I factor out that x minus y squared, I'll be left with x minus y squared minus 16. And now this is obviously a square. And hopefully everybody recognizes 16 is a square. So I'm going to keep that common factor. And I'm going to factor that into the difference of squares. X minus y, minus 16 will be plus 4 minus 4. How about, is that one okay? How about y to the fifth minus 625y? Does anybody see anything in common here?
Yeah, they both can be taken to the fifth root.
I'm sorry, I couldn't hear you.
They both can be taken to the fifth root.
Well, this is a fifth. I don't think 625 is. But do they both have a y?
Yeah.
So let's change that to y times y to the fourth minus 625. We're subtracting. It's not a cube, but does everybody recognize it? It's a square. I could take y square and square it to get y to the fourth. Does anybody know what I could get square to get 625? If you're not sure, take the square root of that number to see. Square root of 625 is 25. And so that's going to give me y squared plus 25 times y squared minus 25. Am I done yet? Or can I still factor that last one? And that last factor is still the difference of squares. So it'll be y plus 5 times y minus 5. And again, these are a little bit more involved than most of the ones on the homework, but you might see one like this. Next, let's look at 81 x to the 14th minus 54 x to the 7th plus 9. Wow. X to the 14th. As we look at that, does everybody see that I have 3 terms? This last one is a constant. And on these two, does everybody notice that 14 is twice 7? So that exponent is doubled. And so in my mind, I almost look at this for a minute as 81 x squared minus 54 x plus 9. The exponent's doubled. I should be able to treat it in the same way. But I guess first we should see, is there anything in common? Is there a number that goes to into 81, 54, and 9 evenly?
No.
9, beautiful. When I take out the 9, I'm left with 9x to the 14th minus 6x to the 7th plus 1. And now I'm going to try to factor that trinomial into 2 binomials. I guess because it ends with positive 1. I know these are both 1s. I know my signs are the same, and they're both subtraction. I know we're going to have x to the 7th times x to the 7th. That'll give me the x to the 7th in the middle. And when I multiply them, I'll get that x to the 14th. How do you folks want to factor the 9? Keeping in mind that we want that 6 in the middle.
Three.
3 and 3, beautiful. And again, if I want to check by foiling, first would be 9x to the 14th. Outer would be minus 3x to the 7th. Inner would be minus 3x to the 7th. Last would be plus 1. And the minus 3 gives me the minus 6. So I've got it. So notice that when the leading term's exponent is double the middle term's exponent, it will usually be factorable. So one last one, just to make sure you realize that sometimes their bark is worse than their bite. What if I have 16x to the 2/3, whoa, plus 32x to the 1/3, whoa, plus 16. Again, let's start by trying to make our numbers smaller. Is there anything that goes into 16, 32, and 16 evenly?
Eight,
Anything bigger?
16.
16. Try to get that largest number out. And so that leaves me with 1x to the 2/3 plus 2x to the 1/3 plus 1. Now, I know those fractional exponents can be a little bit unnerving when you first see them, but it's in descending order. And does everybody notice that the first exponent is double the second? So let's see. In order to get x to the 2/3, it'll be x to the 1/3 times x to the 1/3. In order to be a positive one, my signs will be the same, both plus signs. And 1 will be 1 times 1. And we're done. So there we go. I think that's about as challenging as factoring is going to get this semester. Are those okay? If so, you might be wondering, why do we need this factoring? Other than being a mental exercise like Jeopardy, why do we need to undo multiplication? And we're going to find that it's life skill that comes in handy when we try to solve equations higher than first degree. And it's also going to be a life skill with where we're going next, rational expressions. And when we talked about rational numbers, we looked in and saw that word ratio in the middle. And we said that it was a ratio or a fraction made out of integers. A rational expression is going to be the ratio of algebraic expressions. Or usually the ratio of polynomials. They're sometimes referred to as algebraic fractions. And we're going to find that in many ways they behave like other fractions. Some examples, we could have something as simple as x over y. We could have something like 2 over 5x minus 10. We could have something like 3x plus 4 over 7. We could have something like 9x plus 6 over x squared minus 5x plus 6. So they're just fractions where the numerator and the denominator are polynomials. when we look at them, the first thing we want to know is what's the domain of the expression. And we had said that the domain is the replacement set for the x values. So it's like, well, what can those x values be? We also look at it as being defined as all values for which the expression is defined if we're not given a domain. And so in order to answer that, we have to think about where is a fraction defined. And with fractions, they're defined for an awful lot of things. The only thing that's undefined is a zero denominator. The other thing that's undefined that we'll talk about later, doesn't really pertain to these, but we need to mention it, is if I have a negative radicand, if a radical has an even index. We can't take the square root of a negative number. But right now we're going to focus on that zero denominator. So to find where a rational expression is defined, we're going to work backwards and see where it's undefined. We're going to set the denominator equal to 0. We're going to solve the resulting expression. And the domain will be all reals except the solution to that, the solutions that we get. So let's look at some examples. What is the domain of each of the following? First expression that we looked at was x over y. And so y equals 0 will be where it's undefined. So for the domain, I'll say that y cannot equal 0. And we can write it that way. Or, I guess if we wanted to, we could use our interval notation. It can be any number smaller than 0 combined with any number bigger than 0. Next, if I look at that 2 over 5x minus 10, then I'm going to start by setting that denominator equal to 0. Now I want to solve that equation. So let's add 10 to both sides, giving me 5x equals 10. And then dividing by 5, I get x equals 2. And so that's where it's undefined. If I'm asked for the domain, I can say that x cannot equal 2. Or if I want to put it in the interval notation, it's any number smaller than 2 combined with any number larger than 2. Next rational expression we looked at was 3x plus 4 over 7. So again, we're going to set the denominator equal to 0. Hey, wait a minute. 7's a constant. Does 7 ever equal 0? I don't think so. So here, this is never undefined. We could say that the domain is all real numbers. Or in interval notation, anything from negative infinity to positive infinity. Last one is something that we haven't really talked about. We will be getting into in a much greater depth next unit, but where I have 9x plus 6 over x squared minus 5x plus 6. If I'm asked where it's undefined, I'm going to set that denominator, the x squared minus 5x plus 6, equal to 0. And now, again, where we're going to be going, this involves that other use for factoring. If we have an exponent on the variable, we want to make one sign 0 to solve the equation. And then we're going to factor for x squared, it will be x and x. My signs are the same, both minus. Multiply to 6, add to 5 would be 3 and 2. And then in order for this product to be 0, it means either the first factor is 0 or the second factor is 0. And so solving those, I get x equals 3, x equals 2. So those are values where it's undefined. So my domain would be all numbers except x cannot equal 3, x cannot equal 2. So the general idea, if you're looking for the domain of an algebraic fraction, set that denominator equal to 0. It'll give you an equation to solve. And once you solve that equation, we're going to say that the variable can equal any number except those solutions. Okie dokie? Any questions? Where I hear the word domain and I'm looking at a fraction, I think denominator equaling 0. Next thing we're going to do then is simplify rational expressions. And the way in which we do this isn't that different than the way in which we do it for numeric fractions. For example, if I asked you to simplify 24 over 36, isn't the first thing that you do is look for the greatest common factor of the two? And does everybody recognize that 24 is 2 times 12 and 36 is 3 times 12? And then we can divide out the 12s, and our simplified fraction is 2/3. I'm thinking you might have in a previous life seen that written more like I'm dividing them both by 12 and I get 2/3. Another way of writing the same thing. We're going to use that factored form though with algebraic expressions. So to simplify an algebraic fraction, the first thing that we're going to do is we're going to factor both the numerator and the denominator completely. Then we're going to divide both by any factors common to both the numerator and denominator. And I'm guessing that right now that looks about as clear as mud. Let me know when you guys have that all written and we'll look at some examples. Are you guys ready? Can you hear me? Yep. Can we do an example or do we need to wait? I ask you to simplify 4x minus 8 over x squared minus 4x plus 4. I have a saying. My saying is fractions are fun if you factor first. So we cannot do any simplifying until we factor. Some people make a careless mistake by trying to just start crossing things out. No, it doesn't work that way. We can't have fun until we factor. So I'm going to treat just the numerator as a factoring problem. If I want to factor the numerator, is there anything in common? Just in the numerator. And when I divide out that 4, I get x minus 2. Now I want to factor that denominator. That denominator is a trinomial. It's 3 terms. I'm going to try to factor it into the product of 2 binomials. For x squared, it'll be x and x. Because it's positive, I know my signs are the same, both minuses. And does everybody see that 4 will factor into 2 times 2? Now that I've got each factor, I'm going to say to myself, hey, if I'm comparing the numerator to the denominator, do they have any common factors? Yeah, they both have that factor of x minus 2. And where I say divide it out, it has a net effect is just crossing it out. But they have to match exactly. And if they match exactly, we can divide them from both. And my final answer will be 4 over x minus 2. So instead, if I want to simplify x squared minus 8x plus 16 over 3x minus 12. Again, first thing that I want to do is factor the numerator completely. The numerator has 3 terms. I don't think there's anything in common to all 3 of them. So let's try to make some binomials. I'll do the hard part. X squared is x times x. My signs are the same because the last one's positive. They're both minus signs. How do you folks think we should factor that 16 to get the 8 in the middle? You're both 4? I think I heard. Now let's look at that denominator. In that denominator, is there anything in common?
The 3.
The 3. And when we divide the 3x minus 12 by 3, we're left with x minus 4. Anything common between the numerator and denominator? Anything? X minus 4s. And so my final answer will be x minus 4 over 3. And so the questions where they ask you to just simplify a rational expression, really, all you're doing is practicing your factoring. And when you practice your factoring, I think the crossing out part is fun. If things match up, factors only, if factors match up between the numerator and denominator, I can cancel them out. Please notice I have to take away the entire factor. There is a special case. What if I have x minus 2 over 2 minus x? Do you notice that they're very similar? They're both subtraction, but the subtraction is reversed. If subtraction is reversed, where I have x minus 2, and I didn't want that parentheses there, I'm sorry. 2 minus x. Notice that if I will put those parentheses in there. If I add them, they add to 0. They're opposites. 1 is negative 1 times the other. And so they will always simplify to negative 1. In general, if I have a minus b over b minus a, that will simplify to negative 1. Be careful though. If I have a plus b over b plus a, is everybody all right? That one's just going to be positive 1 because in addition order does not matter. It's only when I reverse the subtraction that I get the opposite. And so let's look at an example that's a little bit more involved. Let's say I have x cubed minus 8 over 4 minus x squared. X cubed minus 8, when we factor that, like we just did, it's the difference of cubes. I'll have x minus 2 times x squared plus 2x plus 4. 4 minus x squared is the difference of squares. It'll be 2 minus x times 2 plus x. And so now here, when I look at whether there are any common factors, notice that these two are opposites. So if I cancel them out, I need to multiply by -1. And so my final answer will be put a negative sign out in front of the fraction. X squared plus 2x plus 4 over, I guess I could write that as x plus 2. Again, because that numerator does not factor, I cannot reduce it any further. And what's really cool is if we know how to simplify fractions, we pretty much know how to multiply fractions. So to find the product of rational expressions, you remember, if I have a over b times c over d, to multiply, I take numerator times numerator over denominator times denominator. So it's the product of the numerators over the product of the denominators. And so after we would do that multiplication, we'd reduce. Well, you know how I had said with rational expressions, your life is always easier if you factor first. To multiply two rational expressions, the first thing we're going to do is we're going to factor each numerator and denominator completely. And then after we multiply across, we'll simplify the product. And that idea that fractions are fun if you factor first, and the fun part is crossing out. So let's look at an example. Let's look at 6x plus 9 over 3x minus 15 times x minus 5 over 4x plus 6. When I see this problem, I see this as 4 factoring problems. The first numerator, is there anything in common? 3, leaving me with 2x plus 3. That denominator, is there anything in common? 3, and we're left with x minus 5. And now we're multiplying it by, look, x minus 5 doesn't factor. And how would 4 times x plus 6 factor? 2 times 2x. Oh Lord, I miswrote, I apologize. 2 times 2x plus 3. And because we're multiplying and we multiply straight across, we cannot just look at that as one big fraction. We've got it all factored. So the fun part is, okay, is there anything in common? Does anything match up?
Yeah.
What?
X minus 5.
x minus 5. Beautiful. Anything else? 2x plus 3. Beautiful. Anything else?
3,
3, 3. So everything from the numerators divided out, we're left with 1. In the denominator, we're left with 2. So our final answer is a half. I do believe in my labs, in these questions, they also ask where is it undefined. They might word it as what values must we exclude. And over here, we've got to remember that the denominator cannot equal 0. So I'm going to worry about when does x minus 5 equal 0? When x equals 5. And when does 2x plus 3 equal 0? Let's see, 2x would be negative 3. So x is negative 3 halves. So we exclude x equals 5 and x equals negative 3 halves. Or it might say x cannot equal, and they'll fill in the blanks with 5 and negative 3 halves. And you notice that the multiplying isn't very much different at all from the reducing. It's just that we got to do that factoring process at least twice as much. How's it look? I know usually once we start looking at things like this, the factoring becomes a little bit clearer to people because now it has a purpose. So looking at my clock, and I think it's about that time. So I'm going to stop sharing, stop recording.